All right, so here is our warm-up for today. Our topic today after the warm-up is going to be apply our knowledge of exponentials and logs to specific situations. It's going to be a word problem day. But for now, we're going to pause the video here and give you about 5 minutes to complete 2 warm-up problems. So if you didn't finish 7 and 8 yesterday, well, not yesterday, sorry, the last time we met, do 7 and 8. If you already did those, do the problems in red for numbers 1 and 2. Okay, so here are the answers to 7 and 8. We'll give you a minute to check yourself. Pause the video for just a minute to check. I'm going to do one upgrade. We don't really write the base 10 when it's a log base 10, so your answer should look, say, log of 90 minus 1 divided by -3. Okay, then for the other two, if you did these, there you go. Now you can see the problem with the answers. We'll pause the video here for you a minute to check those answers if you did those two. So today we are going to apply our knowledge. So we're going to do some word problems specifically around Newton's law of cooling. So we're going to pause the video here, and what I need you to write down is this whole equation and what all the variables stand for. So we're going to pause the video to give you enough time for you to write all of that down. You do not have to memorize this equation. What Newton's law of cooling is it's used to model temperatures of an object where they're going to cool down. So a hot cup of coffee is hotter than room temperature, so the coffee will cool down. A hot bath, taking something out of the refrigerator and into room temperature. So those are just some specific examples, and we're going to work through some problems together. So here's the first problem. We're going to pause the video for you to read the problem, write down what these variables are before we do any of the other work. So write down this entire problem, set up, write down this equation again, and now we'll pause the video for you to pull out what these variables are. So if you need it, from what we wrote down just prior, here is what it lists as all the different parts of that equation. So 90 degrees Celsius is the initial temperature, so that's T sub 0. The outside temperature is 18 degrees Celsius, so that's the ambient temperature, that's T sub A. 2 minutes is our time, so that's T. And we want to know when the cup of tea will reach 65 degrees. So that is our T of T. That's the final temperature. I'm sorry, yeah, the final temperature of the cup. All right, so our first problem is determine the value of the decay constant. For this, we are going to use a calculator. So if you have your calculator handy, take that out. All right, so we're going to set up our equation. Here's the model so that our only variable is K. So my ending temperature is 65 degrees. That's going to equal the ambient temperature or the outside temperature, which is 18, plus the initial temperature minus the outside temperature times e to the negative K times 2. All right, we'll get to our calculator in just a minute. So now we have to solve for K, kind of like the warm-up. We're going to combine these values. If you want to use your calculator for the arithmetic, go ahead. I'm going to subtract 18 to the left. I'm running out of room. I'll go over here. I'm going to divide by 72. And so that leaves us with 47 over 72 equals e to the negative 2k. So to get this exponent out of, to get the variable out of the exponent, we need an ln because we have an e. So we have the ln base e of 47 over 72 equals negative 2k. We're going to divide both sides by negative 2. And so k is, now, if we have an assessment without a calculator, this would be calculator ready. This is a calculator ready answer. Where we just then don't have our calculator and we can't type it in. But now I have my calculator, so let's actually calculate it. So I'm going to type ln 47, divided by 72, divided by negative 2, and we get 0.213. K is 0.2. I don't like the way that's written. Sorry, guys. 0.213. There we go. All right. Part B says write a function in t minutes. So now that I have k, we're going to go back with all our pieces up here, and we're going to fill in the equation, leaving t as the variable. So temperature over time was the ambient temperature plus, and now we already did this 90 minus 18, so we're going to simplify that to the 72, e to the negative 0.213 t. Okay, so then part C says graph the function. So we're just going to make a sketch. I'm going to use my calculator again. So to graph, we hit y equals, and I'm going to type 18 plus 72 e to the negative 0.213x. Now, if I just hit graph, I'm not going to see anything because my window is 10 by 10. So I'm going to hit the window button. And I'm going to change, so x is time. Just going to leave that as the negative 10 to 10. But my y max, because the coffee started at 90 degrees Celsius, I'm going to round up and say, let's start at 100. So I put an image of my window here, and then I'm going to hit graph. We can see, here's what our graph looks like. If I hit trace, it tells me the y-intercept is 90. That's that initial temperature. And then I'm curious, is the asymptote going to be 0, or has there been any transformation? Notice where I'm moving my mouse. Any transformation to this exponential graph that will change where the asymptote is located? So if you hold down the right arrow while you trace and look at the Y's, I should not see that Y go below 18. It's going to get really, really close to 18, but never below it, because that was that vertical translation. So we have a horizontal asymptote here at 18. Use the graph to describe how the temperature decreases over time. So for that, I would say it's an exponential decay approaching the horizontal asymptote of Y equals 18. All right, so here's number 2. I've crossed some of these out. We're going to pause the video here for you to write down the setup of the problem, and then we'll go through parts A, B, C, and E together. Okay, so from our problem, we've got this hamburger meat, and it's removed from the freezer at 0 degrees Fahrenheit and placed in the fridge at 38 degrees. So this is the initial temperature that it starts at, and 38 degrees is the ambient temperature of the fridge. 6 hours, that's our T. The temperature is 12, that's T of T. All right, so our part A is determine the decay constant. Part B is write a function, graph it, and then we'll answer part E. All right. Okay, so I need some room to find the decay constant. So let me make some room here. And that's not gonna work. Okay, we'll just do it down here. All right, part A. The ending temperature is 12. The ambient temperature is 38. The initial temperature was 0. Still the ambient temperature is 38, and then E to the negative K times 6. Okay, so now let's start solving for K. So this will be negative 38. Like if I condense this portion, it's negative 38. So instead of writing plus a negative, I'm going to go minus 38 e to the negative 6k. So then to start solving, I'm going to subtract this 38 to the left. You cannot combine these because this 38 is multiplied by the e. So we're going to subtract 38. Divide by negative 38. So what's nice here is the negative divided by a negative is positive. So 26 and 38 are both even numbers. I really want to reduce those as I keep going. So I can reduce both of these by 2. Now I can change to an ln to keep solving. So ln of 13/19 is negative 6k. Divide by negative 6. So this is a calculator ready answer, but now I'm actually going to get my calculator and calculate that since we're going to write our equation. All right, so K is 0.063. So part B said, write your function. So T of T is 38 minus 38 e to the negative point, I forget, 0.063 t. Graph it and how long. Okay, so for the graph, now I'm not going to bother with the calculator this time, because I know my horizontal asymptote will be at 38. That's the translation. And then I've got this double reflection. So this is an exponential decay reflected. So instead of going this way, I'm going to reflect it and go that way. And the starting temperature was 0. So here's our graph. If you want to graph it, you can. Sometimes it just takes longer to type the buttons and mess with the window. Hey, that doesn't even look that great. Let me go lower. So you get that general shape, goes through the origin, has that horizontal asymptote of 38. And so then part E is, how long will it take the meat to reach 32 degrees? So we're going to take our equation and set it equal to 32. And now we solve for T. So the first step is subtract 38 from both sides. Divide by negative 38. So negative divided by negative is positive again. We can reduce both of these by 2. Convert to an ln to solve. Oops. Divide by negative 0.063. And let's see how much time it'll take. And I think it said round to 3 decimal places, 29.299 minutes. All right, here's a third example. Now they're giving us the equation for a cup of coffee. Here's our equation. So I want you to write down on your paper this whole function. And then for part A, what is the temperature of the coffee at the beginning of the experiment? So I want you to find the initial value when T is 0. So we're going to pause the video here for you to do that. Okay, so the answer for A, so f of 0, 112 e to the 0 plus 68, because this is 0 times the decimal is still 0. E to the 0 is 1. So 112 plus 68, you can use your calculator, you can add it up. 180 degrees Fahrenheit. All right, part B, what is the room temperature? So now that I know my initial value, T sub 0 is 180, and we have this coefficient of 112, or this 68, we have two ways to figure out B. So here's the first easiest way. T sub A, that room temperature, is the constant, it's 68. If I didn't want to use it that way, what I could say is, oh, I know 180, which is the initial temperature, minus the ambient temperature has to give me 112. And I could solve for it. So negative TA is negative 68. So then positive 68 is your answer. All right, part C, after how many minutes is the temperature 140 degrees? So we're going to pause the video here, and I want you to try part C. We've done that now twice. I just wanted to get some more room. Okay, so 140 is our ending temperature. To solve for T, we're going to subtract 68. Divide by 112. And what's neat, so in your calculator, if you go divide by 112, you get that crazy decimal. So if you hit math, enter, enter, it reduces the fraction for you. It's kind of nice. I'm going to convert to an ln. Don't forget that negative in there. And divide by negative 0.08. The T is 5.523 minutes. Okay, if there is any time left in class here, you can pull up this assignment in the module and start it now. So here is what the assignment looks like in the module, and it is due on the 6th.